Hola, muy buenos días a todos. Bienvenidos a nuestro seminario de Laboratorio de Microtecnologías y Sistemas Embebidos. En esta ocasión nos va a presentar su avance de temas Daniel Casañas. Sus directores de tesis son el doctor Marco Antonio Ramírez y el doctor
Luis Alfonso
Villavares. Daniel es alumno de doctorado. Este ya es su segundo semestre. Le damos la palabra a Daniel.
Thank you very much, Doctor. My thesis subject is about AI Computer Accelerators, but this semester I focus on the development of a bit of a Python infrastructure to actually research hyperdimensional computing, which is one of the techniques that I'm interested in to develop, let's say, embedded intelligence, i.e., artificial intelligence in embedded systems, low resource constrained, low energy powered devices in general. So this is a bit of a progress report for my second semester. Everything I did was pretty much software. I did nothing about hardware, fortunately. But let's try in the third semester to present something at least in FPGA. All right. Let's have a little introduction here. So as I was saying, my thesis work focuses on hyperdimensional computing for AI in embedded systems. But hyperdimensional computing is a relatively new technique. What it's all about? It's about computing with large vectors in the order of 10,000 dimensions. It's a bit simpler than it sounds. It's a bit mathematical and all that. And it was developed by a Maestro called Caneva in the mid-1990s. And the technique leverages the properties of very high-dimensional vector spaces. And it provides a simple, efficient, and robust mathematical framework around which we can model cognitive tasks. This is a brain-inspired algorithm, and it aims to model, as I said, cognitive tasks like memory and learning, of course. It has been proven that it has some resilience against noise because we can vary some of the elements, at least a third of the elements in these hypervectors, and we can still recognize what the hypervector represents. So as I said, it's a technique that it's been developed for artificial intelligence. The hypervectors, which are the minimal units of computation for hyperdimensional computing, are elements of a so-called hyperspace. A hyperspace, we call it S. And they are defined in accordance with a vector symbolic architecture, which is just a fancy name to say these hypervectors have certain elements and certain properties. And of course, the main constraint for these hypervectors is that they have to be at least 1,000 dimensional. We can go beyond 1,000 dimensions, but not below. It's customary to say that our hypervectors are at least 10,000 dimensional, but as we're going to discuss further in this talk, we can accomplish some very interesting results with around 5,000 or 7,000 dimensions in our vectors. And as I said, these hypervectors are defined by something called a vector symbolic architecture, which is just a way to say our vectors are, let's say, binary, or let's say they are binary in a sense that we have vectors with -1 or 1 elements in all dimensions. And these vector symbolic architectures also define a set of operations between these vector elements. And an interesting property, and pretty much the spine of why this algorithm or these techniques work, is that in very high dimensional vector spaces, the elements of this hyperspace called hypervectors, I said, are quasi-orthogonal. So let's say that let's take a couple of hypervectors at random from the hyperspace, and if we compare them in this space, we can say that they are pretty much very, very far from each other. if we measure the distance in this 10,000 dimensional space between 2 points at random, they are pretty much, let's say, in opposite sides. So this is like the spine of why these algorithms work, because of orthogonality with random elements. And well, as I said, in general, all vector symbolic architectures define a set of vector operations between hypervectors. In general, they are called binding, bundling, and permutation. The implementation by variables, if we remember, we can have binary hypervectors. We can have these hypervectors with the -1 and 1 elements. But there are other vector symbolic architectures where the elements can be even complex numbers, integers, floating points, and so on and so forth. But in general, these are like the three main operations between hypervectors. Binding is a binary operation, between two hypervectors, and it's similar to multiplication as we know it. Integer multiplication, floating point multiplication, it's just like a product. And the resultant point, if we have point A in hyperspace and point B in hyperspace, and we multiply them or we bind them, the resultant point, the product point or the bind point, is far from its operands. Again, we have a point here, A, we have another point here, B. If we multiply them, the result of that multiplication is going to be very far in the hyperspace. Again, this is a 10,000 dimension, or at least a greater than 1,000 dimension space here, so it's like very, very hard to imagine a space like that because we only live in 3 dimensions, but bear with me. We have bundling, which is very similar to addition, but it's not quite like that. We're going to discuss the details further in the talk. And the resultant point of this addition between 2 points in the hyperspace is going to be very close to its operands. So again, let's say we have a point A and point B in the hyperspace, and if we bundle them, then the resultant point is going to be very much closer to the operands. So that's like the bundling thing. We can also say that this operation does not conserve orthogonality, and binding conserves orthogonality, but that's quite a fancy way to say it, like they're far or close, And last but not least, and the least used operation between hypervectors is permutation. So the permutation is a unary operation. We only need a single hypervector, and it's very similar to a circular shift. So let's say we have some binary vector. It doesn't have to be a hypervector, and we shift those elements to the left and to the right. But the element at the end of this vector is going to come all the way around to the top over here. So it's very much like a circular shift in binary logic, but again, it's in 1,000 dimensions or even 10,000 dimensions. And the resultant point is far from the original point. Again, this is a point in the hyperspace. If we rotate the elements of this point in this hyperspace, the resultant point, which is going to be different, is going to be very, very far from the original point, even though we can do a shift of 1 or 2 elements, and the result is going to be even farther. All right? And well, as I said, there are a couple or a handful of vector symbolic architecture available. In my case, I'm going to consider only the main ones, which are like the most richest ones, which are a so-called BSA, or binary splatter codes, which is pretty much a binary hyperspace, and multiply, add, permute, which is a binary sort of hyperspace, but with elements in the -1 range. So let's consider these two vector symbolic architectures with their proper elements. And in this table, I'm going to summarize the operation between these hypervectors. In the case of binding, with binary hypervectors, we have that it is implemented with a logical XOR. a logical XOR like we know it from digital logic. It's very simple. The bundling operation, it's what is called a threshold addition. And in the permute case, we have both circular shift in both cases for binary sputter codes and multiply add permute vector symbolic architectures. But something that I missed in the past slides is that a vector symbolic architecture not only defines a set of operations around hypervectors and what the elements of these hypervectors are, but it also defines a measure of similarity between the points in the hyperspace. As I said, we can like measure the distance between these points in the hyperspace, but we don't know actually how. And this is defined again by the vector symbolic architecture. In the case of the binary sputter codes or the binary hyperspace, 0, 1 elements, we have that the Hammond distance is a measure of similarity. If we, again, want to measure the similarity of how far, how close two points in the hyperspace are, we can measure the Hammond distance between these two elements. And of course, the bigger the Hammond distance, the farther they are in the space, and conversely. And in the case of the multiply add permute hyperspace, which is binary again, but with -1 and 1 elements, we have that a measure of similarity is the cosine similarity, which is similar to draw some pair of vectors over here, and we have like a vector sum. And you know, you guys remember your physics classes and that sort of thing. Well, it's very much the same thing. So this is a summary of what we're actually dealing with in the mathematical sense. It's very theoretical up to this point. But like the nitty-gritty of the whole thing is hyperdimensional computing-based classification, which is my actual thesis subject. So let's say we want to classify a dataset with hyperdimensional computing. This is like the de facto application of this technique. And as you guys know, classification is performed traditionally with neural networks and support vector machines and, you know, like the traditional algorithms. But researchers have developed a very robust and very simple algorithm to classify datasets with hyperdimensional computing. And it's not that hard to understand once you get the hang of it. So let's say we want to classify signals that are in, well, analog signals that are in the frequency domain. This is just like a very simple application. And these are signals. These are signal bins here. So let's say we want to classify them. Well, the first step in order to classify these data sets composed of analog signals is that for each signal bin in what is called a feature vector, for each feature here, we want to generate a random hypervector that is going to represent its position. It's called index hypervector or position hypervector or idea hypervector. It's all the same. All right. Thank you very much. So we're going to generate a random hypervector for each one of these, let's say, signal bins here. One for this one, one for this one, one for this one, and so on and so forth. Yes. So let's say if we have a feature vector of 617 features, like we are going to see in a data set further in the talk, we're going to have to generate 617 random hypervectors for all the signal to be transformed in a hyperdimensional space. And then we have to generate some so-called level hypervectors in order to quantize this information bins here, like we do with analog signals in analog and digital converters. If you guys remember of the digital logic classes, if we want to convert an analog signal into digital, we have to quantize the signal with some discrete values here. And this is pretty much the same thing. But instead of quantizing our signal with a certain number of bits. We're going to quantize them with hypervectors. So these positions over here in the y-axis are going to be represented by hypervectors. Now then, how can we actually transform the signal into a hypervector? Let's say we have this information bin over here. In order to transform this bin into a hypervector, or transform this bin into hyperspace, we want to multiply the ID hypervector over here, which represents its position, against the matching level hypervector here. Of course, these bins are not going to match perfectly into this or these hypervectors, so that's the quantization thing. But then again, it's pretty much the same thing as quantizing a signal. We multiply this hypervector here by this hypervector here, and then the resultant hypervectors of multiplying this and this and this and this and this and this and so on and so forth, and then add it together all the way up until our feature vector is done. That is when transforming our feature vector into a hypervector finishes, which is pretty much what I have here. So let's say we have, again, we want to classify a data set, and this data set is composed of analog signals. We generate some index hypervectors at random, and we generate some so-called level hypervectors. The first one is generated at random, and the next ones, or the subsequent ones, are generated in a way that the neighbors are very similar to each other, similar in the sense that they are very close in the hyperspace, but as we go up in this axis, this one is farther in the hyperspace than this one. This one is even farther in the hyperspace than this one, in a way that if we take the first one and the last one, they are pretty much in opposite sides of the hyperspace. They are very, very far from each other. But that's magic, and that's why it works. So, well, up to this point, we have already transformed a feature vector in some analog 2D space into hyperspace. Now, we want to actually do some classification work. How do we do this? Well, let's say that our feature data is already labeled, which is called a supervised learning. So we want to bundle together all the hypervectors that match a same label. So let's say we have a transform hypervector here that has some label, and we take, or let's say we cluster all the hypervectors that represent a certain class, and we bundle them together. And the result of that is going to be called a class hypervector or a prototype hypervector. And we do the very same thing for all the remaining hypervectors of matching classes. So when we finish to train our model in order to do classification, we're going to end up with a series of class hypervectors that represent a certain class. And that is going to be stored in a so-called associative memory. Each one of the elements of this associative memory, which can be implemented in hardware as a content addressable memory, are going to be hypervectors that represent a certain class. So when we finish with all the training data, we're going to have a populated associative memory that has all the other possible classes that there are in our data. So this is like only the first part of the whole thing. The next thing that we're going to have to do is the actual testing. Testing is it's pretty much done in the same way. We take a feature vector that represents a query vector. Let's go here. Let's say that we have a feature vector here. It's not transformed yet. We transform them or encode them into hyperspace, and then we're going to have a query hypervector. So classification here is done in a very simple way, as I said. And what we're going to do here is we want to measure the Hamming distance or the cosine similarity between the query hypervector and all these class hypervectors here, in a way that the one that has the minimum distance, or the one that has the largest similarity between all of these ones, the index of this hypervector is going to represent the class of, the query hypervector, or the label where it belongs. And because we want to do have a, how can I say it, like a scoreboard of how many hits or how many misses we have here when we query this hypervector against all of these vectors here, and that value is going to represent their accuracy. And that's pretty much it. As I said, it's very simple. It's very fast. It's very easy to implement, at least in software. In hardware, I don't think so. But in at least in software, it's very simple to understand. Now, the third and last part of my talk is going to deal with what I actually did during the semester, which was do with the development of a Python framework in order to actually do this whole thing that I've already talked about. So the first thing that you guys may think when I say Python and anything is that there may already be some Python framework or Python library that already does this, and you will be correct. The point is, or the only caveat is, that the only one that existed that is actually being developed right now is very complicated, and it is quite convoluted. And by the time I wanted to do some research, some actual research with this thing, and do some testing in order to see like the lacking points on the algorithm, it was pretty much impossible because it is so overly cluttered and complicated. So I said, like, okay, I'm going to develop my own tools, and with the only rule that it has to be very simple and it has to be very fast, which I didn't accomplish, but that's another thing. And it has to work, of course. So I put some effort in developing a so-called library called HDCPy. That's why I named it. And it's, as I said, it's a very easy to use Python library that implements only the basic hyperdimensional computing functionality to do HDC research, but only the most basic components. I'm not going to implement like fusion with hyperdimensional computing and neural networks like this, guys. Very sorry to the HDC guys, but you guys are impossible, sorry. And it's based entirely on a very well-known Python library called NumPy that deals with vector computations, matrix multiplication, in general, like linear algebra stuff. But that's what I did. The highlights of this library is that it's very simple and the implementation is very straightforward. Only we support the most widely used vector symbolic architecture, as I said, binary sputter codes, and multiply add permute. And of course, only the bare minimum functionality is implemented for hyperdimensional computing classification. Of course, there are pitfalls. The main pitfall, or the most concerning pitfall, is that it is a bit slow. And certainly it needs further optimization. That's my bad. Error catching is in bare minimum. And that's because I'm not a Python expert. I actually learned Python during the semester. Bear with me, please. And there may be redundant functions that account a certain type of data. As I said, the main application for classification is analog data. But as we're going to see further, we can have other kind of data. So there may be several functions that can look redundant in the whole perspective of the things. And so far, I have tested a handful of datasets. Here we had isolate, use-har, splice, and cardio. I chose these ones because they are very, very popular and they are the most cited in the literature out there. I'm not going to like reinvent the wheel here. These data sets are all in pretty much every data set out there, in every paper out there that cites something about hyperdimensional computing. So these are like the most popular, but there are more. I'm actually still looking for data sets, popular data sets, to test further. But these four is what I have. And as I said before, we not only have like a lot of data to classify. In the very particular case of DNA, these DNA strings, they are like just strings of characters, so it's not like an analog signal or anything. So I had to implement certain functionality. As I said, it may be redundant to classify DNA encodings, which we're going to see some very interesting results further. And something that I came up with is that there are some very interesting ideas that may impact the functionality of the whole classification thing. In fact, I researched the impact of dimensionality and the number of quantization levels for error signals, of course, in the classification accuracy, which are going to be over here. So as I said, I explored the impact of the dimensionality and the number of quantization levels in the classification accuracy. So if we take a brief look at this image, we can see that as long as we are above 4 quantization levels, the whole thing doesn't change that much. That's it. I mean, if we have like 3 quantization levels, it's still acceptable, but it's not that, it doesn't quite cut it. But if we are above 4 quantization levels, then we can achieve like something above 80% classification accuracy with pretty much no effort. But the other thing that I wanted to explore is the effect of dimensionality in the whole thing. And as we can see, if we choose 6,000 or 7,000 dimensions for a hypervectors, the classification accuracy doesn't change that much, does it? So up to 6,000 or 7,000 dimensions, in this case bits, because I use binary hypervectors, classification accuracy doesn't change that much. So we can conclude that as long as we have 4 quantization levels and at least 6,000 dimensions, our classification accuracy can be above, or very, very well above 80%, which, as a rule of thumb, if our classificator is above 80% accuracy, it's considered a good enough classificator. There's some other data set, and again, it's very much the same thing. This data set doesn't have quite an impact, or the classification accuracy doesn't have quite an impact with when we vary the number of quantization levels. But then again, we can see that as long as we are above 4 quantization levels and around 6,000 or 7,000 dimensions over here, we can at least achieve 80% of classification accuracy, at least. Then we can say that these are like good enough specs for a hyperdimensional classificator. These are only 2 examples. I'm not going to plot the whole thing with graphs and that sort of thing, but yes, and well, oh my god, it didn't compile. Well, I'm very sorry. I did some other thing over here, but well, just let's imagine that I did the actual work, and and well, similar tests were conducted with all data sets. And as I said, we can conclude that these are like the very minimum parameters to have a good enough classifier. And the next area that I wanted to explore is how does classification with hyperdimensional computing works against more traditional algorithms like neural networks and support vector machines. And these are my results so far. Of course, there are cases where neural networks and some more traditional algorithms still accomplish very above our implementation accuracy results. But we can see that we are not very far from these very well developed approaches. So for the isolated dataset, our classifier achieves at least 86% accuracy against 86% for a neural network and a 96% of a support vector machine. For this one, the UTH dataset, we can accomplish 80.87% accuracy. For a neural network, we accomplish 86.63%, and a support vector machine accomplishes 99%, nearly 100% of accuracy. Now, this is when it becomes very, very interesting. For these splice and cardio datasets, which, as we can see here, have a very, very low feature count, with hyperdimensional computing, we can achieve nearly 100%, or in this case, 100% classification accuracy. So we don't miss any data. We can classify the whole data set correctly. And this is very, very interesting. And of course, support vector machine also accomplishes 100%, but we're interested in hyperdimensional computing. So we can see that as long as a feature count is low, I have yet to actually define what low is in these terms. We can accomplish nearly 100% classification accuracy. So this is very, very interesting. And the simulations are blazingly fast. Like in 2 seconds, we're done, like this. So as I said, we can achieve nearly 100%, or in some cases 100% classification accuracy, as long as our feature count is low enough. But there are data out there, or there are data sets out there that don't have such low feature count. So how can we alleviate this problem? There is a technique called retraining, which, like the name suggests, it's about retaining the whole model in order to up these numbers a little bit for hyperdimensional computing, which unfortunately hasn't been implemented yet in my library, but it's like a coming soon feature. So in conclusion, we can say that hyperdimensional computing is a useful technique for lightweight classification tasks. It's very simple when it comes to the actual algorithm, at least in software, and its mathematical properties call for a hardware implementation that leverages the characteristics of these techniques, mainly low power and potentially its application on embedded environments with low power and very, very noisy atmosphere. And of course, it's very limited in the sense that if we surpass what is called a hypervector capacity, our classification accuracy is going to be a bit lower than expected. This capacity thing is a subject that has already been researched by one of my colleagues here. We haven't been able to actually tackle the subject yet in our implementation. And of course, a potential pitfall when I developed some hardware implementation is that the memories can be quite large, because again, we are dealing with 10,000 dimensional vectors here. So if we have let's say, a feature count in a certain data set of 617 features, we have to multiply those by 10,000, and then those by the number of, the number of quantization levels. So it's going to be a very, 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 very huge memory here. So those are like the potential pitfalls when it comes to hardware. Memories are quite large. Of course, large memories imply a larger energy dissipation, and of course, as I said here, we have to compare our query hypervector with a bunch of potential hypervectors here. So we need a multiport CAM memory. As we know, multiport memories are not very well seen in the hardware atmosphere. So this is like another pitfall, that we have to have very large memories with a very large port count. So, and of course, our data is going to be mainly retrieved by sensors in an embedded environment. So we have to take that into account. So far, the hardware implementations out there don't take into account that our data is going to come from sensors, don't take into account the large chunks of memory that we need to store all these sort of things, and they don't take into account the number of ports that are actually needed. So this is like a bit of a hole in the research that we have to tackle. Thank you very much. Please, questions are welcome.
Okay. Gracias, Daniel. Muy bien, pues preguntas, sugerencias. Adelante.
La primera explicación creo que estuvo muy bien cuando hiciste lo de la HDC, de cómo funciona el cómputo hiperdimensional.
Ajá.
Pero mi pregunta era más enfocada a si todos los datasets que incluiste para hacer las pruebas entre las redes neuronales y las máquinas de vectores de soporte y el HDC eran datasets como binarios, o sea, como de sí, ¿no? O eran multiclase.
No. Sí, algo que me faltó poner en esta tabla que está por acá es que justamente tienen un número variable de clases. ¿Dónde está? Hostia,
Ajá, en esas.
Sí, algo que me faltó aquí en esta tabla fue que el número de clases no es solamente de sí o no.
Ajá.
Sí. Por ejemplo, en este dataset que es el isolate, que es sobre clasificación de letras por medio de voz,
Ajá.
tiene pues solamente el número de letras del abecedario, son 26, o bueno, al menos 26 o 27, bueno, lo que sea. Vaya, el número de letras, pues. Este de Usihar tiene un poco menos, tiene 4. Se supone que se trata de clasificar actividades humanas por medio de acelerómetros y todo eso. Entonces, los datos te pueden decir si estás caminando, si estás sentado, si estás acostado, bla, bla, bla. Son como 4 o 6 clases. En este de Splice, que es sobre clasificación de cadenas de ADN, son 3 clases. Y en este de enfermedades cardíacas en infantes recién nacidos, se llama cardiocotography, algo así. Este tiene solamente 3 clases, 3 o 2 clases. Ajá. Entonces digamos que hay un número variable de clases. Otro criterio que no mencioné justamente para elegir los datasets es no es que fueran solamente datasets que estuvieran realmente documentados en la literatura donde se han utilizado estos algoritmos, sino que también tuvieran un número variable de clases. Ajá. Entonces son muchas variables las que hay que considerar. No solamente tenemos que considerar el número de features que tenemos en cierto vector, sino también el número de clases y todo eso, ¿no? Entonces digamos que estas conclusiones parciales tratan sobre de que siempre y cuando tengamos un número pequeño de features para transformar, y siempre y cuando estemos por debajo del límite de lo que le llaman la capacidad del hipervector, entonces podemos tener resultados muy buenos o extremadamente buenos. Pero vaya, es otra cosa que tenemos que explorar.
Sí, lo preguntaba porque, por ejemplo, a lo mejor se pudiera hacer otra de los detalles que pudieras incluir en el futuro para que resalte más la técnica que estás ocupando, porque si a lo mejor haces ya la comparación de cómo se comporta con la multiclase, porque me acuerdo que, por ejemplo, las redes neuronales ocupan un dataset muy grande de entrenamiento, ¿no? Y las máquinas de vectores de soporte, yo en su momento las usé y me acuerdo que algo que le da en la torre a las máquinas de vectores de soporte es la multiclase. Entonces, a lo mejor si el HDC se comporta mejor con multiclase, aunque queden tablas con el accuracy, pues a lo mejor se pudiera ver ahí la mejora, ¿no?
Exactamente, justamente aquí podemos ver. Bueno, yo no, pero ustedes sí pueden ver, es que ya se empañaron mis lentes. Ustedes sí pueden ver que al menos en los datasets donde sí tenemos un poquito de más de clases, como que sí estamos, ahí por ahí, como que ya le queremos pegar, ¿no?
Ajá.
Pero así siguen ganando. Como tú dices, tendría que encontrar un dataset que estuviera documentado allá afuera en los artículos y además que tuviera un número grande de clases para ver justamente lo que tú dices.
Sí.
Pero sí, esa es una muy buena sugerencia, muchas gracias.
Sí.
¿Alguien más que tenga preguntas, sugerencias?
Gracias. Mencionaste una operación llamada binding, me parece,
Sí.
que es bueno, se indicó que es similar a la multiplicación, pero similar ¿a qué tipo de multiplicación? ¿Es algo así como un producto punto?
No. Es similar a la multiplicación porque es literalmente una multiplicación en esta arquitectura simbólico-vectorial. Cuando existen hipervectores de este tipo que tengan elementos como -1, 1, el binding se implementa literalmente como una multiplicación, literal. Y en el caso de vectores binarios, tal cual, con ceros y unos, el binding se implementa con una XOR lógica, digamos bit a bit. Entonces, literalmente la
Pero, o
multiplicación.
sea, si es una multiplicación vectorial, o sea, para vectores de mucha...
No. Es una multiplicación, digamos, elemento a elemento. Digamos que es similar al producto punto, pero sin la parte de la suma reductiva.
De
O sea,
la suma.
no sumas todo, o sea, simplemente multiplicas elemento a elemento y ya está. Ajá.
Sí, para allá iba mi pregunta,
Sí,
porque si no, si fuera como el producto punto, y mencionaste que los vectores de alta dimensionalidad son cuasi ortogonales, se te irían a cero, ¿no? Si hicieras esa suma de reducción. Bueno, muchos de ellos se irían a cero por ser multiplicación de ortogonales.
Sí, porque serían, además de eso serían, bueno, si haces la parte de la suma, pues ya no sería un vector, sería una escala. Ajá, pero no. O sea, sí es una...
bit a bit. Ajá.
Sí, es bit, bueno, elemento a elemento en general.
Sí. Gracias.
De nada.
Bueno, mencionabas en la diapositiva 21 las memorias grandes, que eso podría ser una desventaja, un pitfall para el simulador que estás implementando, ¿no? Entonces, ¿has considerado cómo el tiempo de lectura de estas memorias grandes puede impactar en el desempeño de tu simulador? ¿O ya lo implementaste ese retraso? ¿Cómo cuantificar ese retraso en el tiempo de lectura?
No.
¿Trabajo pendiente?
No, sí, justamente algo que no mencioné aquí porque es que otra cosa que tengo que considerar a la hora de hacer una implementación en hardware es la latencia que hay entre que yo hago una solicitud de memoria para traer un hipervector
Claro.
y entre que yo la reciba para poder procesar, por ejemplo, un elemento o un valor que viene de un sensor. Y ese es un problema. ¿Por qué? Porque como son elementos muy grandes, seguramente no voy a poder traerme todo el hipervector entero, voy a tener que partirlo en pedacitos. Entonces, al partirlo en pedacitos, en un cierto momento va a llegar un pedazo, en otro cierto momento va a llegar otro pedazo, pero tengo que hacerlo suficientemente rápido para poder cachar al sensor. Eso, o tengo que bajarle, digamos, la potencia, bueno, más bien tengo que bajarle la frecuencia a la memoria para yo poder acoplarme a los sensores.
Claro, que tenga la misma frecuencia el sensor.
Sí, justamente.
Otra opción posible sería bajarle la resolución al sensor. ¿Para qué mapear una señal con 10 bits y a lo mejor con 3 bits basta? A eso, pues, como bien sabes, se le llama la cuantización, pero con escasos bits. Scarcity se le llama. The scarcity of data.
Sí,
entonces, la idea es de que tú puedes obtener, por ejemplo, un modelo de una red neuronal que tenga el mismo nivel de precisión, no sé, si con 10 bits tiene 98%, a lo mejor con 4 bits alcance un 97 punto y algo. Sí, entonces deberías también explorar esa idea de el cuello de botella no sería tanto en la lectura, sino también en la cuantización y cuantizar con tamaños de bit más pequeños.
Sí, claro. Desde luego, esas son cuestiones que no se han considerado hasta ahorita en los artículos que he consultado, porque digamos que están asumiendo de que los datos ya vienen, digamos, ya preparados, están listos ya en las memorias y simplemente yo lo que hago es hacer la inferencia. Pero la idea de implementar esto en hardware es que esté haciendo la clasificación en vivo. Entonces, en ese intento de hacer la clasificación in situ, pues no voy a tener, digamos, pues el dataset ahí entrenando, ¿no? O quizás ya tenga preentrenado una cierta memoria, pero aún así no me escapo del hecho de que tengo que obtener los datos de los sensores. Entonces, eso es algo que todavía no se considera, digamos, actualmente. Simplemente se han quedado en que ya tengo los datos ya, digamos, listos, estáticos, y simplemente yo hago la inferencia. Gracias.
Sí. ¿Alguien más? ¿Alguna pregunta más? ¿Comentario? ¿Sugerencia? Bueno, pues le agradecemos a Daniel. Gracias.